This video is on chapter 22, part 2, and we're going to focus on example 265. We are given a matrix and we want to find the four fundamental subspaces of the matrix. So, first of all, the first step would be to take our matrix and put it in reduced row echelon form. Our matrix is already in reduced row echelon form for this example, so we didn't have to do that. I want to call your attention, as I mentioned that, to Theorem 241. Theorem 241 says that we do not change the row space by using row operations. So had this matrix not already been in reduced row echelon form and we put it in reduced row echelon form, we do not change the row space. We could, however, change the column space. We won't change the dimension of the column space, but we might change the column space itself. So we look at this matrix, and it is already in reduced row echelon form. It has 5 columns. Notice that one of them is I and R3. Another one is J and then K. So if you look at the first, the third, and the fifth column, these vectors span R3. So the column space is R3. The second and the fourth column are irrelevant as far as the span goes. Now, we know that the column space of A and the null space of A transpose are orthogonal complements in R3. And since the column space has dimension 3, the null space has to have dimension 0. So the null space of A transpose is simply the 0 vector in R3. The row space of A is simply the span of the 3 rows. These 3 rows are linearly independent. Notice that this matrix has rank 3. So we have 3 pivots. We have 3 pivot columns, the first, the third, and the fifth. And we have 3 rows. So the rank of this matrix is 3. The rank is the number of pivots. The rank is also the dimension of the row space. Since we know the dimension of the row space is 3, and we have these 3 linearly independent rows, we know that these 3 rows span the row space. Remember the rank plus nullity theorem. The rank, which is the dimension of the row space, plus the nullity, which is a dimension of the null space, has to equal 5, because the matrix has 5 columns. Rank plus nullity is n, where n is the number of columns. So that means there are 2 linearly independent vectors in the null space, and we can use these 2 linearly independent vectors to span the null space. I left this blank because I want to work with you again to see how to find vectors in the null space. So first of all, let's look at our first free column. Our first free column is the second column. So what we do is we put a 1 in the second place, and we put zeros below that. The row space and the null space are subspaces of R5. So we have our second position is a 1, everything below that is a 0. Then we come over to our pivot column right here in the 2, 2 place, and we look up and we see a 2, and so we put a negative 2 in the first place. This vector is in the null space of A, and you can check that. Then we need to find a second vector. So let's find our next free column. Our next free column is the fourth column. Now when we build this second vector, we're sort of going to pretend that this second column doesn't exist. So we're going to look at this fourth column and treat it like it's a third column. So how do we do that? Well, we come to the fourth place, we put a 1 in the fourth position. We put zeros in all the positions below 4, which in this case is 1. Now we put a 0 in the second position. And now we have 2 spots left. So we come back over to our fourth column that we're going to pretend is a third column. So we're going to sort of pretend this column doesn't exist. And so now right here in what we would think of the 3-3 position, we have our 1 that we put in the vector over there. And now we look up and we have 2 more positions to fill. So we look up and we have a 4 and a -3. So for our vector, we will write a -4 and a +3. And so our null space is the span of these 2 vectors. And we have 3 vectors spanning the row space, 2 vectors spanning the null space. 3 plus 2 is 5. And we will always have rank plus nullity as a number of columns. Now, I'm going to work with the column space, and I'm going to work with the null space of A transpose. We already know what that is, but we're going to pretend that we don't know that this is the null space. So we're going to we're going to take A transpose and we're going to put it in reduced row echelon form because we're going to look for its null space. We don't have to look for its row space because its row space is the column space of A. But we do want to find the null space of A transpose. So we take A transpose and we put it in reduced row echelon form. The reduced row echelon form has rank 3. We have 3 pivots. So we know that the null space is trivial because we have as many pivots as we have columns. So we found the null space. But the reason I wanted to do this example was to illustrate the point that I made earlier. These 2 matrices do not have the same column space at all. This column space is the same as the row space of A. This is the column space of A transpose. We weren't asked to find the column space of A transpose, we were finding the null space of A transpose. But these 3 vectors do not span the same subspace of R5 as these 3 vectors. If you look at any vector that would be made by these 3, the 4th and 5th components would always have to be 0. That is certainly not the case if you're going to use these 3 vectors and look at their span. So again, row operations can change the column space. So putting this matrix in reduced row echelon form changed the column space. It did not change its dimension. The column space of this matrix and the column space of this matrix, they both have dimension 3, but the spaces themselves are different.